Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a final video on Law of Cosines for a trigonometry course, and we're going to be talking about navigation problems. It gets its own video, mainly because they are very popular when using the Law of Cosines, and it's a little bit confusing because there's different books and different people use different languages to talk about different things. And so I'd like to kind of pull things together here and make it somewhat concise. So let's talk about some differences in definitions. Heading, bearing, and direction. We're not really going to focus on direction, honestly. We're going to just focus on heading and bearing. Those two are navigational words that are used quite frequently in navigation, and to know the difference between the two is kind of important to be successful in at least a trigonometry course. So heading. Heading is the angle of intended travel measured clockwise from due north. Now, I put the words clockwise and north in red because, well, that is significantly different than all of the trigonometry you've been doing. So if I said that there was a ship that was heading, let's just give an example, a ship that was heading 75 degrees, or was moving at a heading of 75 degrees, or whatever it may be, we in trig would think, well, I'm going to measure 75 degree angle from the positive x-axis, which is technically due east. But that's not how it's done in navigation. A heading of 75 degrees is measured from due north and turns or opens clockwise. So that's kind of a frustration. I totally get it. But this direction right here is the heading of 75 degrees. This is done in aviation, mainly in aviation, actually. And so you could have things like a heading of, let's do a heading of, I don't know. Let's do something slightly large, like 190 degrees. A heading of 190 degrees. Again, you start by facing due north, and you'd rotate clockwise past 90, past 180, until you're facing 190 degrees, which is actually somewhat southwesterly. So that is what heading is. It's unfortunate that it just differs from what our trigonometry is, but then again, in navigation, it's not that you're doing hardcore trigonometry in navigation. You do use trigonometry though, but it just makes, I think, more natural sense for the human mind to think of things as due north being 0 degrees and then turning left or right, or basically turning as a clock would through an angle. The second one, which is bearing, is one of my favorites, but it also tends to throw people off. Bearing is not exclusively used in ship navigation, but it does get used in ship navigation and hiking a lot. And how is it defined? This is actually a harder definition to really write down to be accurate, but this is the best I could do right now. Bearing is the acute angle of travel measured from due north or south. Notice in red here, the very important statement, it is an acute angle. So it's less than 90 degrees. And it's measured from due north or south, just depending on how you'll get that angle to be measured to be acute. And the notation for this needs its own definition. So the notation If you're measuring from, say, due north, you'll start with north, you'll have some number of degrees, and then you have to state, because if I'm facing due north and I'm measuring an acute angle, it could be this way or it could be that way. So we're going to end this notation with the direction that we rotated through, either east or west. So west or north by so many degrees east, or you could have faced south and turned through so many degrees west or so many degrees east. So this is probably the best I could do with a definition. So let's go ahead and see how this works. So this works much better with just an example like this. Let's suppose that you're facing this direction and you turn this way by, oh, I don't know, let's say 23 degrees. Then if that's the case, you are facing south, you turn 23 degrees in the westerly direction. So south by 23 degrees west. West is this way, east is that way, obviously north, and then south. The bearing notation always starts with either north or south and ends with either east or west. The angle between those two is always acute, never negative, always between 0 and 90 degrees. So another example, let's just say that you started by facing north and you went through this, and this angle might be 80 degrees, right? So this would be face north, turn by 80 degrees to the easterly direction. So north by 80 degrees east. Just to remind you, this makes no sense. North by 130 degrees east. You're not going to do that. So please do not do that. The angle must be acute. The way you would say that is you would say face south and turn through 50 degrees east. That would give you the same facing, south by 50 degrees. South by 50 degrees east is the same statement. In fact, a better statement. So notice the differences in these definitions from your base trigonometry. This is the only time in trigonometry you'll be measuring from something other than a horizontal axis. When you're doing heading and bearing problems, you're always measuring from a vertical axis, which presents a level of confusion for students. So just to remind you, throughout all of trigonometry, you are measuring from the horizontal x-axis until you get to these types of problems, application problems involving navigation, where you're measuring from a vertical line. And so just be aware of that as we move forward. You are not going to measure from vertical lines for anything other than these. So let's dive into a few examples here. An airplane flies 220 miles with a heading of 40 degrees and then flies 180 miles with a heading of 170 degrees. How far is the plane from its starting point and at what heading from the starting point? That should have said. And then round your answers actually to the nearest tenth. I've read the problem. Now we need to draw a picture to truly understand the problem. So I'm going to plot, because I could easily tell I'm going to need some space here. I'm going to plot my drawing a little bit lower on this page. So I'll pause the video and do that. And actually I didn't do very much, right? I just put a dot with an S because I actually want to describe every step that I'm doing here. So that's our starting point. And the plane is going to move at a heading of 40 degrees. In other words, face north and turn through an angle of 40 degrees. Well, that's easy for me to do because I have a little ruler here. So I'll draw a little north angle there. And that's critical that you always do that. Just draw a tiny little line going north as a reference. And then I'll turn through an angle of 40 degrees. So 90 minus 40 is 50. So that's just going to be right about there. So I don't have to be this accurate, but I like to be this accurate. So the plane is flying in this direction for 220 miles. Let's just pretend as though 220 miles looks like the following. So let me write down here that this is the 40 degree angle. Right. And I'll put a little dot at the layover point right there. It's not really a layover, but That's just every time that a direction is changed, you want to put a little dot there, and actually you'll want to put a little north-south axis. You'll see why in a moment here. So once the plane gets there, it then flies 180 miles with a heading of 170 degrees. Well, I'm going to put a little north-south line there because I need to measure, and in fact, maybe I should do my north-south line in a different color, something like brown or something like that. Do a little north-south line there. And I need that because, again, the plane is going to turn through an angle of 170 degrees clockwise. And so that would get this plane to face all the way over to here. Let me keep going. Right about. So that's, if you see that 80 degree angle, that's 90 plus 80. So that's 170. And then it's going to travel for, I forget how many miles. Let me look up here. 180 miles. So let me go ahead and measure that out. There we go. That's 180 miles. We'll just pretend. And I didn't bother writing it before, but I should. We had a 220 mile length here. So I'm going to write 220 miles there. And just to let you know, that brown angle right here was 170 degrees. Every time that I get to that stopover point, I just go ahead and draw a vertical line. In fact, the plane arrives here. And now what we want to know is, what is the distance for the plane between its beginning and its ending? And what would be the heading? And let me make sure that I read the problem correctly before I state this last piece. So let me turn off my ruler and see how far is the plane from its starting point at this moment and at what heading. Now, I'm assuming that since the plane, well, at what heading? That's a tough one to respond to. How far is the plane from its starting point and at what heading from its starting point, I think is really what it means. So I want to not only know what is this red distance, but I want to know what is the heading from the starting point to where the plane is at the end here. I'll call that E for end, start to end. And then we'll call this point up here, I don't really care, we'll call L for layover. Okay. So let's go ahead and we've drawn this out as accurately as we can. Let's talk about why we do all these vertical lines in here and how important they're going to be for all of your navigation problems. I hope you understand that vertical lines are parallel to each other. Specifically, this vertical line in brown right here and this vertical line, which I'll go ahead and do like this in brown right there. Those two vertical lines are parallel to one another. That's critically important that you understand that. Because if they are parallel, this black line right here, the angle it makes here is equal and opposite to the angle it makes with the vertical line there. These are alternate interior angles from your geometry. So we know that if this angle right here is 40 degrees, then its alternate interior angle right here is 40 degrees. We also know that on the other side of that vertical brown line, 170 degrees is taken right here. So therefore the remaining angle here must be 10 degrees because they're supplementary angles. So it's 180 minus 170. This gives us the actual angle opposite that red line to be 50 degrees. That angle right there is 50 degrees. Now this is a real big mess, right? Seems like it's very messy. So what I end up doing is I just redraw my triangle in a cleaner state down below, although I'm not going to be accurate. I'm just going to quickly kind of jot out a triangle. And this is vertex S, this is vertex E, this is vertex L. We know that vertex L, it has an angle of 50 degrees. We know this side is 180, that's side little s, and we know side little e is 220. We're going to use that information and build a table. Let's see, L S, and E. Angle L is 50 degrees. Let's see, side L we don't have. This side L right there. That's the side we want. Side S we do have. It's 180. And side E, little e, is 220. And you can see, again, we don't have a completed row, so we're going to use law of cosines. This kind of goes with the previous video in the series, which is the solving application problems using involving non-right triangles using the law of cosines. That was a previous video. So we'll go ahead and find that missing side length L by using the law of cosines. L squared is equal to S squared plus E squared minus twice S times E times the cosine of the angle opposite side L, which is 50 degrees. And then you take the square root of both sides. L is going to be roughly equal to, and we'll hop over to Desmos to do this computation. One thing I should note here is because we have two questions in this problem, we're going to be asked to find this distance that we're in the middle of finding, but we also need to find this angle in red here. And because of that, I want to save this length that I'm computing just in case I need it to help me find that red angle. So when I use Desmos, I'm going to save the value that I get in Desmos for that length as the letter L. Here we are in Desmos. I'm just going to type L is equal to, oops. And remember, to be in degree mode, Desmos automatically starts us off in degree mode, so that's okay. We have 180 squared and then plus 220 squared. Let me make sure that I'm not making any mistakes. Minus 2 times 180 times 220 times the cosine of the angle opposite L, which was 50 degrees. And we get a distance of 172.9 roughly. So you can see I've written that 172.9 right there. I've also filled it in our table, and I've also written it in our picture. Now, the other part of the question, how far is the plane from the starting point? Well, maybe I should write that here, 172.9 miles. So I'll box that up. But we also need the heading from the starting point to the plane. So I'd love to know what this red angle is. Well, I happen to know that part of that red angle is the 40-degree angle right there. So as long as I can find this part right here, then I will add 40 to it, and that will give me the heading of the plane from the starting point. So again, heading is measured from due north. So we'd have this 40-degree angle right here plus whatever this additional angle is, and that would be the heading from the starting point to the plane. Well, that's the same as this angle right here, S. So I'd love to find the angle S. And now that I have a complete row, we should use the law of sines. And I'm telling you, you should use the law of sines. But the caveat, remember, when you're using the law of sines, when you have a complete row, and you're using the law of sines to find another angle, you should always use the law of sines to find the angle opposite the shortest remaining side. Luckily, that's the angle we want to find anyway. So I'm going to use the law of sines to find this missing angle. If you don't know why we're using the law of sines to find the angle opposite the shortest remaining side, I highly recommend that you watch my law of sines videos, specifically the spot where I talk about the ambiguous case for the law of sines. It's very, very important to understand that. But luckily, the angle we're trying to find is already opposite the shortest side. So law of sines is going to be perfect here. Also note that the value we have in this row is an approximated value. So I'm going to use my saved value in Desmos, which is the non-approximated value, to help me with this part. That's why I saved it as a letter in Desmos. So let's see, law of sines. The sine of that angle S is to its opposite side as the sine of the angle L is to, sine of the angle L, 50 degrees, is to its opposite side, lowercase l. And notice I'm not actually writing in 172.9 because I want to use the value in Desmos that I saved. I'll multiply both sides by 180 and take the sine inverse of both sides, and you get that the sine, or s, is equal to sine inverse of 180 sine of 50 degrees divided by lowercase l. Let's go ahead and see that in action. So we're back here in Desmos, and I want my angle S to equal the arc sine of, and we have 180 sine of 50 degrees, and we're going to divide that by lowercase l, the L we had saved up above. So that L that we have saved up above is in an exact form, which is exactly what we want here, and so we don't suffer as much from rounding errors. So we get 52.9 degrees for S. Now this actually presents a kind of an interesting problem. I really dig this. So 52.9 degrees is what S is. Now remember, that's not actually the angle we want to respond with. S is this interior angle here, 52.9 degrees. Now, one of the things you should realize when you're drawing things out by hand, which is basically what I did here, your drawings are never going to be super accurate. And I want you to notice that this angle, this actual full angle in red right here, is 40 plus 52.9. That's actually greater than 90 degrees. So my drawing is not perfect here. It should actually be slightly down, right? I mean, that's way over exaggerated, but it should be slightly down. It should be beyond 90 degrees or beyond horizontal. This is going to change how we respond in this problem. This makes this problem a little more interesting to me. So let's see. We faced north. If we're going to say, oh, hey, how do I get to the airplane from the starting point to its ending point? I would tell somebody, normally, if you were talking about heading, you would say, oh, you face north and you turn through an angle of, 92.9 degrees. 92.9 degrees. It's slightly less than horizontal. Now, it doesn't make actually a big deal in this problem, other than the fact that it is just kind of interesting. So I'm going to say heading here is 92.9 degrees, but it will make a big difference in our bearing problems. If this was a bearing problem, then we'd have a major kind of, I don't want to say major, but a slight modification at the end, because in bearing problems, you want your angles to be acute. Well, in this is a heading problem. All the words say heading, heading, heading. So you don't have to worry about that. You can have non-acute angles. But if it was a bearing problem, we would not be able to work with that 92.9 degrees. We'd have to say face south and turn through an angle of 87.1 degrees east. So we'll talk about that if we have to deal with it in the bearing problems. But this problem is completely done. Really cool problem, great use of both the law of cosines and the law of sines, and wonderful, wonderful use of heading within a problem and being able to draw just vertical lines and using alternate interior angles. You're going to be using that quite a bit with navigation problems. Now, I find that just one navigation problem is terrible, just because it's not enough, generally speaking. So let's try to do as many as we can in a short period of time. Two planes take off at the same time from an airport. Okay. The first plane is flying at 246 miles per hour on a course, or a heading, that's what that means, of 135 degrees. The second plane is flying in the direction of 175.0 degrees at 357 miles per hour. Okay. So notice the words they're using here are not exactly heading. They use the word course and direction, which they really intend to mean heading. You just have to interpret that. That's just how it goes. Assuming no wind currents are blowing, how far apart are these planes after 2 hours? Now, the idea of wind currents blowing is going to come into play in a future video. We'll start talking about vectors and how a wind vector will push a plane into what we call a resultant vector. But for now, we're just going to keep things simple and say the direction they were aiming for is the direction that they're actually going. So their true course and their intended course are the same. So let's see. We have a plane that's flying at 246 miles per hour on a course of 135. And both planes, by the way, start at the same point. So let's go ahead and at least put a dot in space here and call that dot S. That's their starting point. And I will face, that S is going to get in my way. I'll draw a vertical line here. And the vertical line, I'll just put a little north-south here in brown. There we go. And the first plane is going to head at a course of 135 degrees, moving at 246 miles an hour for 2 hours. Well, that's just 246 times 2, so we can compute that pretty quickly. So there we go. Plane number 1 is heading 135 degrees, and for 2 hours at 246 miles per hour, that's 492 miles. I'm actually going to write the word miles because M to me means meters. All right, and then we'll go ahead and take a look at the second plane. The second plane is flying in the direction of 175 degrees. It's probably better that I use a different color for the second plane. So there we go, and the angle that that plane was flying at, right, 175. So I'm just going to draw this out as a 175. I'm going to point at it like that, 175 degrees, and it flew at that in that direction at 357 miles per hour for 2 hours, which is 714 miles. 714 miles is that length right there. So I have that drawing. Assuming no wind currents are blowing, how far apart are these planes after 2 hours? That is, what is that red distance? That's really what we want to know. All right, we have two side lengths there. We need just one more piece of information. Luckily, in this problem, the missing angle between those two side lengths is pretty easy to find. This angle right here is 175 minus 135. So that's 40 degrees. And now we're just ready to go. So this is a pretty fast problem. Very nice problem. And so you could label this, I'll label this little s, and I'll label the other sides. It actually doesn't really truthfully matter. I'll call this side A, this side B. So this is angle B and this is angle A. And now I build my table. I'll build my table off to the left just to be different. A, B, and S. Angle A we don't know, angle B we don't know, but angle S we do. It's 40 degrees. And then side little a was 492. And side little b is 714. And what's cool about this is that you really do get to see that all of these law of cosine problems are the same problem over and over and over again. And I just quickly wrote out what I'm going to pop into my calculator here. And I'm not even going to bother hopping over to Desmos because we've done that enough times. I'm just going to write out the answer. And I get roughly 462.2 miles. That's the distance they are apart after 2 hours. Really kind of a fast problem, honestly. And if you're working on an exam where your instructor, your professor does not allow a calculator, then leave your answer just like that, without the approximation, just like this, the square root part. That is perfectly fine. That's very much acceptable if you're not allowed a calculator. That's called exact form. Don't bother figuring out what 492 squared is and 714. That's arithmetic. You don't need to do that. You wouldn't do that. I haven't done that in any of my videos when I'm doing this. I just grab a calculator. When I'm about to grab a calculator, I don't do my arithmetic. Now let's get into some bearing problems. And if you've noticed, I skipped an example because really the example 13 was actually the same style of example as example 12. So I just decided to not do it. All right. Alice sets off on her hike from the lodge, I guess there's a lodge, at a bearing of south by 74 degrees west After 3.4 miles, she changes her bearing to south by 13 degrees west and continues hiking for 6.8 miles. Find her distance from the lodge at this point. And what is the bearing for her to go back to the lodge? Really good, solid problem here. When you have a clean sheet of paper like this and you're trying to decide where to plot your initial point, pay attention to the directions here. She's heading south and then west, and then heading south and further west. So if you plot a point way over here, you're going to run out of room because she's going to go this way and then this way some more. You're just going to run out of room. If you plot a point at the bottom of your paper, again, you're going to run out of room because she's heading south. So I would plot at the upper right-hand corner here. That's that's where the lodge is. And I'll draw in a vertical line so that we have our vertical line, right? So let me go ahead and do that. So the bearing problems and the heading problems, you still draw in vertical lines there for the north-south. It's very important that you do that. So from the lodge, she's going to face south and then turn through an angle of 74 degrees in the westerly direction. So there we have it. She's face south, turned by 74 degrees in the westerly direction, and she hikes for 3.4 miles in that direction. This will not be to scale, by the way. She then, once she reaches the end of that 3.4 mile mark, we plot a point and we again draw in a vertical axis there. It doesn't have to be a long, it shouldn't even be a long vertical axis. It should just be a short little line. But enough so you can see you have two parallel axes there because you're going to want to use alternate interior angles eventually. But from that point, she changes her bearing to be south by 13 degrees west. So she faces south here. Let me draw that in. And she turns through an angle of 13 degrees to the west. So let me draw that in. This is 13 degrees right here. 13 degrees. Just like she faced south and turned 74 degrees west before. And then she hikes for, 6.8 miles. So I'll just put 6.8 on this edge. And she stops. And at that point that she stops, the question is, what's her distance to the lodge from that point? So what's this distance that I'm slowly trying to put together here? And I'll do that distance in red. All right, there. So what is that distance? And what's her bearing to go back to the lodge? So she gets to some destination and she just wants to go directly back to the lodge. Or maybe she broke her leg and she needs to give somebody directions to go back to the lodge for her or something like that. So from this point, again, every stopping point you want to put in a vertical line. So I'm going to put in a vertical line right here in brown. Let me do that. You don't have to use brown. I'm just using brown because I can. And now I don't need my ruler, so I'll turn off my ruler. And we want to know what is her distance, and then finally, what's her bearing to get back to the lodge. The distance, you don't have everything you need here because you need 3 pieces to a triangle to solve a triangle. And right now, if I were to draw this triangle off to the side, well, sort of, right? That's not correct to scale, but I don't really care. I only have 2 real pieces of information, 3.4 and 6.8. So I'll need another piece of information. And that comes from using alternate interior angles. For example, if this angle, let me use a highlighter. If this angle right here is 74 degrees, then this angle right here should also be 74 degrees because they're alternate interior angles of parallel lines. So I am going to go ahead and call this, this angle right here, 74 degrees. So again, the alternate interior angle idea is very, very important because then you would say, oh, well, if that's 74 degrees from here to here, then this remaining angle is a supplementary angle. It's the supplement of 74 degrees. So 180 minus 74 would be 106 degrees. That's what that little angle there is. And if you look at that 106 and add 13 to it, you would get your angle right here. 106 plus 13 is, what is that, 119? So this is 119 degrees right here. So that's why I always draw these vertical lines in, because you're going to be using a lot of your alternate interior angles and all that fun stuff. So now that I've done that, I can just focus on this for a bit and I can solve this triangle. I want to find this distance right here. So I'll label these. I'll call this angle A. So this is side A. I'll call this angle B and this angle C. It actually doesn't matter how you label them. So angle A, B, and C. Just building my little table of values here. Angle A is 119. Side A we don't know. Side B we do know because that's opposite angle B, so that'll be 6.8. And side C is opposite angle C, which is 3.4. And you could see, again, the same old law of cosines. We don't have a complete row, so we're going to use law of cosines. And we are just going to use the relation that the A is equal to the square root of B squared plus C squared minus 2BC times the cosine of the angle opposite side A, which is 119 degrees. So notice that I immediately just went for the square root rather than saying A squared is equal to, I just said A is equal to the square root because we've done this enough at this point. We quickly compute this, and I don't need, well, actually I do need to use Desmos because this is a two-part question. The first part is finding that distance. Once we find that distance, we're likely going to use it to help us compute an angle. So I do want to save that value. So let's go ahead and hop over to Desmos and save that distance as A. So we're in Desmos here. I'll say A is equal to square root of, and then type all this stuff in. And I typed it in very quickly. And let's go ahead and call that, let's see, 8. Oh, that's 9.0, right? Because it rounds that. The 5 in the hundredths place will round that 9 up by 1. So it'll be 9.0 miles. And I've written that in there. I suppose I could write it in my table since that's going to be helpful. So I'll say roughly 9.0 miles. And again, I give this advice every single time. So one thing you should see, you have a complete row, so you can use law of sines, right? To find an angle. And you should probably ask, like, why is he trying to find an angle? It's because we want to know not only her distance back to the lodge, which was roughly 9.0 miles, but also we want to know the bearing to get back to the lodge from the point where she stopped. From this point, I want to know the bearing. Well, we have two vertical lines here, the ones you can see on the screen, here and here. And because they're vertical, they do have alternate interior angles. This 13 degrees is alternate interior angle to this angle right here. So this will be a 13-degree angle. And you could see this person, what is her name? Is it Alice or something? Yeah, Alice. Alice, to get back to the lodge, she will face north and turn through 13 plus some angle to face the direction of the lodge. So we need to find that plus some angle. And that plus some angle is angle C here. So we want to find this missing angle C. Well, we have a complete row in this table, which means we can use law of sines. Just remember, when using law of sines normally, you want to use law of sines on the angle opposite the smallest remaining side. Now, I say normally because the fact is law of sines will only return angles that are acute, less than 90 degrees. And if you try to find the angle opposite, the angle opposite the largest remaining side, you risk finding an angle that might have been obtuse because it's opposite a large side. But in this case specifically, we already have one obtuse angle in our triangle. You can't have more than one obtuse angle in a triangle, so neither of the remaining angles are going to be obtuse. They're both acute. So technically, if we were to try to find angle B here, we'd be safe. And luckily, we don't have to worry about that because we're actually finding angle C, but we're safe in both cases because the obtuse angle is already stolen for angle A. That's just a heads up. All right, so let's go ahead and use law of sines to find angle C. Well, we know that the sine of that angle C is to its side as the sine of angle A is to its side A, which I have saved in Desmos. So angle C is equal to the sine inverse of 3.4. Whoa, what just happened there? Of 3.4, I should probably zoom in, times the sine of 119 degrees divided by A. Now I'll hop over to Desmos and finish this out. Arc sine of 3.4 times the sine of 119, and we're going to divide that by A, and we get 19.4. So C is roughly 19.4 degrees. I will zoom out. I'll insert that 19.4 right here, so we know it's 19.4 degrees. Probably the largest mistake I'll see here is that people will just say, oh, she moved to get back to the lodge, she's going to go north by 19.4 degrees east. No, she goes north by 13 plus 19.4. What is that? 32.4 degrees. So 32.4 degrees east. So north by 32.4 degrees east, because she has to face north, turn through 13 plus that extra 19.4. So that's a 32.4. So north by 32.4 degrees east and 9.0 miles away. There you go. That's the full problem. A really good bearing problem. Most bearing problems kind of operate this way. We'll finish out this video with one last bearing problem and call it a day. Now, this final bearing problem is a bear. Forgive the pun. But it's a bit of a trudge through this because there's a lot to visualize here, and we are going to do our best to make an accurate visualization of this. So a helicopter makes a forced landing at sea. The last radio signal received at a navigation station gives the bearing from the station to the helicopter as north by 55.4 degrees east at an altitude of 1,050 feet. That is, the helicopter was originally at an altitude of 1,050 feet before it crash landed. An observer at the station confirms that the angle of elevation to the helicopter just before descent was 22.5 degrees. So we're really synthesizing a lot of our language from trigonometry up to this point. Luckily, there's a rescue boat that's due north of the station, and the bearing to the helicopter from the boat is south by 56.4 degrees east. Final question. How far is the boat from the crash site? This is an incredibly robust problem. And it will, although we've read it, I don't know if we truly understand it. We need to draw a picture. Now, the picture, I'm going to take my time drawing it. I'm going to pause the video and take my time drawing it. And then I'm going to describe everything that happens. First of all, I drew the station and the boat there. S is the station, B is the boat. And the reason why I know that's the way they're aligned is because there's a rescue boat due north of the station. They don't give me the distance. They just say it's due north. So that's the easiest part. The next thing I do is I'm kind of doing things a little bit out of order, but that's just because of the way that my brain thinks. So the bearing to the helicopter from the boat. Let me highlight what I'm reading. The bearing to the helicopter from the boat is south by 56.4 degrees east. So if I'm at the boat, the bearing to the helicopter is, well, they're going to face south. Whoops, that was supposed to be a pen. They're going to face south and turn by 56.4 degrees east. So that's what they do here. This angle right here is 56 56.4 degrees. They face south and turn by 56.4 degrees in the easterly direction. I made this line very long because the intersection of their view and the intersection of the station view will be the crash site. So I just wanted to make it long enough to where there was an intersection that was going to occur. Well, from the station, let's see. The last radio signal received at the navigation station gives the bearing from the station to the helicopter as north by 55.4 degrees east. So from the station, they're going to face north. Again, was supposed to be a pen. They're going to face north and turn by 55.4 degrees to the east to face where the crash is. So I'm going to draw that in right now. There, I've drawn it in. That's 55 north by 55.4 degrees. So north, they face north, turn 55.4 degrees to the east. There we go. And the intersection there is where the crash occurs. So that's the crash site. There we go. Now I'm going to go ahead and erase a few things and kind of recolor a little bit. And the reason why I do that is because we want to know that distance in the end. How far is the boat from the crash site? So this red distance is what we want. There's a lot more information given in this problem than what I've drawn in. The problem is the rest of the information is in a different dimension. Let me say that again. The rest of the information is not given in a top-down view. This is the top-down view. This is as if you're elevated above the ocean. You can see the station here, you can see the boat there, and you can see the crash there. Now there is a different view, not a top-down view, but a side view. And this is the best way, in my opinion, to attack a three-dimensional problem, is to draw two different pictures. It's just much easier. And how do I know this is a three-dimensional problem? Well, helicopter makes a forced landing at sea. We're done with that sentence. We know that's true. Okay, great. Done with it. The last radio signal received at the navigation station gives the bearing from the station to the helicopter as north by 55.4 degrees east. We did all that. But the one thing we didn't do in that sentence was the altitude being 1,050 feet. And if you're looking from top down, well, I can't tell you, I can't draw in right here, like a little dot above this dot, out into your world, out into your screen, to showcase that there's an elevation of 1,050 feet that helicopter was at before it crashed into the ocean. So instead, I do a side view. It's just much easier to do that. So I'll bring up my ruler. I'll just do a side view. And you'll notice something weird about my side view, or interesting, I suppose, about my side view. I use green as the horizontal side, and I could use blue or black as the vertical side. Actually, it doesn't really matter. What's interesting about the vertical side, by the way, is it's vertical versus the horizontal side, which is horizontal. But that vertical side, move this ruler over to the other side, is 1,050 feet. And this creates a right triangle. I hope you would all agree. So let me just go ahead and draw in here a right triangle, if I can do it accurately enough. Well, this is good enough. There we go. There's my right triangle. And here's the reason why I drew this lower leg in green, or the lower side in green. It's because somebody at the station observed the helicopter at an altitude of 1,050 feet before it crashed into the ocean. That S and C is the same thing as this S and C right here. So these are the same S and C's, and they share the same side length, in fact. That green side length here is a top-down view of this side view of the green side length. I hope that makes sense. That's how I would tackle a three-dimensional problem, honestly, in a trig course. It's just much easier. So we've finished this piece of information. I'll cross it out. An observer at the station confirms that the angle of elevation to the helicopter just before descent was 22.5 degrees. That is, somebody at the station looked up at the helicopter and saw this angle of elevation as 22.5 degrees. Why they know that offhand that accurately, I have no clue. But there we have it. So that's done. Luckily, there's a rescue boat due north of the station. We've drawn that. And the bearing of the bearing to the helicopter from the boat is south by 56.4 degrees east. We've done that. So we now have every piece of information covered. Let's go ahead and figure out this problem. Well, if we were only handed this triangle, we were not handed enough. You need 3 pieces of information to complete a triangle. And unfortunately, we've only been given 2. And you might say, no, we have 3 because I can find that angle C. Well, I'm going to tell you 3 angles also don't help you. Because if you have 3 angles, I could make, how do I say this? Let's say you know that angle C, which I'm not going to write in here, but that angle C is 180 minus 56.4 minus 55.4, which is 68.2. So you know that angle C is definitely 68.2 degrees. Well, if this was 55.4 degrees and this was 56.4 degrees, this would also be 68.2 degrees. So notice those 2 triangles have the same exact degree measurements, but they're not the same exact side lengths. So they're similar triangles, but they're not the same size. So knowing all the angles doesn't help you in trigonometry. What helps you is knowing one side and some angles, or 2 sides and an angle. So in this case, we just don't have any of the sides. We'll need a side length. And unfortunately, we don't have one, but I have a link to one of the side lengths over here. I could find that green side length by saying by asking the question, what trig function relates this angle to this side and this unknown side? And that trig function is tangent. So notice I'm going into my right triangle trigonometry. I know the tangent of 22.5, because I have a right triangle, I can use right triangle trig. Tangent of 22.5 is 1050 divided by that side length, which I'm going to call side length B because it's opposite angle B over there. So divided by side length B. I don't want to call that B up there. So therefore B is equal to 1050 divided by the tangent of 22.5 degrees. I am not going to grab a calculator because they didn't ask me what that side length is. Nobody wanted me to respond with, hey, that side length is B or whatever number it is. They don't need to know the distance between the station and the crash. They need to know the distance between the boat and the crash. So I'm going to just write the exact form of this side length right here, 1050 of the tangent of 22.5. I will use that in a few moments in a calculator, but not yet. Now I'm going to go ahead and label all these missing pieces and build a table. My angles are S, C, and B. And, let's see what they've given us. We actually know all the angles. So angle S is 55.4 degrees. Angle C, we could compute if we needed to. And in fact, I think I told you it was 68.2 degrees. And angle B is 56.4 degrees. I'll write that in like this, 56.4 degrees. Great. Side lengths. Well, side length S is actually what we want. Side length C, we don't have. Side length B, we do have. That's 1050 divided by the tangent of 22.5 degrees. Notice how I'm just not grabbing a calculator here. And that's a good habit. Don't grab a calculator till the very end. Good habit. Notice we have a completely filled row. That is, this is not a law of cosines problem. this is actually a law of sines problem. And so I can use that completely filled row to help me find the angle, the side length opposite the smallest angle. Now, that is a little bit of a, how do I want to say that? When you're finding angles, you always want to find the angle opposite the smallest side. When you're finding sides, it doesn't actually matter. You don't have to worry about the smallest side or anything like that. But I have mentioned it in a previous video that, just keep with the habit of finding the smallest, right? So in this case, find the smallest side length. It wouldn't hurt to find either side length using law of sines here. But we're being asked to find side length S anyway, so we're safe. But we would have been safe no matter what. So, all right, side length S is to the sine of the angle opposite that side length, as side length B, which I'll just write as B, is to the sine of its opposite angle, 56.4 degrees. Multiply both sides by the sine of 55.4 degrees, and you'll get that missing side length is B sine of 55.4 degrees divided by the sine of 56.4 degrees. From this point forward, I'm not going to have to come back to this page. I'm just going to go over to Desmos and compute, and that will be the end of it, because we're finding out what is that distance between the boat and the crash site. What is that distance S? So I have no need to come back to this page. I am now going to just hop over to Desmos. Now that I'm in Desmos, you have two ways of doing this. You could either compute B right now if you wanted to. Remember, B was 1050 divided by the tangent of 22.5. You can compute that and then use that in your computation. Or you could have just straight computed side length S is equal to B, which again was 1050 divided by the tangent of 22.5 times the sine of 55.4 being divided by the sine of 56.4. It's your choice. They're the same computation. So you could have saved B and then said B times sine of 55.4 over sine of 56.4, or you could have done it this way. But in the end, 2,505 feet is the distance between the boat and the crash site. There you go. So that is the full kind of lecture on applications involving non-right triangle trigonometry.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.